I'm going to touch on the embedded machine learning software frameworks a little bit. The reason I want to do this is because there are many different machine learning frameworks out there, and you need to understand how to choose the right one for the right problem that you are trying to solve. But before we get there, let's talk about the general ecosystem of what's involved with machine learning frameworks, as they may not all fit on 256 kilobytes of RAM that we have. Let's take TensorFlow and open up the hood and see what's inside. Here is the general architecture of TensorFlow. As you can see, it looks quite complicated, and there are many different pieces to it. For example, there's a lot of high-level code that you might write in Python, or you might use C++, Java, Go, and so forth in order to express your program or your neural network itself. And then you want to actually train it. So you have a distributed execution engine, which is capable of using different computing systems all concurrently in order to quickly train the model. In addition to having the capability of different systems, each of these systems might have different types of hardware. So you might have CPUs, GPUs, or Google Tensor processing units, and you've got to orchestrate all of that execution. Well, you've got to manage all of that capability and execution and heterogeneity of data that you're getting back. So naturally, these systems tend to be quite complicated. And just by the nature, you end up relying on big operating systems. And so these frameworks like TensorFlow or PyTorch rely on operating system capabilities like Windows or Linux, for instance, that are capable of running these. However, these operating systems come with a fair bit of complexity themselves. For example, they have to support virtual memory and the ability to manage multiple threads that are concurrently running on the system. And why am I talking about all of this? Well, remember, we're talking about embedded systems, and which has got a very limited amount of capability in terms of compute, memory, storage, and power. And so we've got orders of magnitude smaller capabilities than these larger platforms. And we cannot have the flexibility of supporting a massive, complex machine learning framework on top of a very simple device. Therefore, we need to think about how we can re-engineer these machine learning frameworks so they're more aptly suited to run on all embedded devices. So typically, when you're thinking about building an inference framework, you're thinking about three things that you need to consider. What kind of model features do you need to support? What kind of software capabilities do you need to have? And what kind of hardware are you trying to support? If we break this down from a model standpoint, what do you need to support? Do you need to support training? The answer is no. We're only going to be doing inference on the device. Do you need to support inference? Obviously, yes. We need to support a wide range of ops. For example, TensorFlow has over 1,400 ops, but in reality, we use only about 50 of the different ops. By the way, when I'm saying ops, I'm talking about things like convolutions and max pooling and those kind of operators. So just from a model standpoint, you need to understand that when you're deploying things on the embedded device, we only need to use a subset of all these features that the engines actually offer. Furthermore, when we think about the software capability, should the tool chain actually support quantization? The answer is absolutely yes. We don't want to typically be running FP32 models. We want to run integer 8-bit models over here. Some small models obviously take up less space, where arithmetic and signal processing can also be done efficiently. Thus, we cannot assume that we're going to have complex operating systems. So therefore, we cannot rely on things like virtual memory support. And that's something we take for granted with big operating frameworks. In addition, when it comes to hardware, we need to think about, do we have support for a diverse range of processors or hardware devices? Well, the answer is no, because typically, on a simple embedded microcontroller, you're looking at a very small subset of processing capability that you need to have. And you need to support, do you need to support many different platforms and features? The answer is yes. You need to build, a framework that can easily target, different vendors' embedded hardware. But, on a single device itself, the heterogeneity is still quite limited. So, for example, TensorFlow Micro, which we are going to learn to use, is one of amongst this whole ecosystem that is starting to thrive of different frameworks of building TinyML. And the reason I'm touching on this ecosystem is because there's a TinyML, engineering that you need to know that's more than just, TensorFlow like Micro, which you're just going to learn in this course. So there's TVM, there's Micro Tensor or UTensor, there's Glow, and there's STM Cube AI. And they're all different types of machine learning frameworks that support different classes of hardware that you're seeing. Let's take, for example, a particular framework and see how they go about deploying the model that's on the left-hand side, all the way down to the custom embedded platform on the right-hand side. Let's take the ST Micro, for example, which is a company that is well known in the microcontroller space. What they often do is they actually take a neural network model that comes in, and they will generate some sort of code in their own proprietary way to run on the embedded system. So let's open that box up and understand that a little bit further. Typically, you have a network that's in PyTorch or in TensorFlow, and you take that into an importer, which imports a model in and builds an internal representation of what the network looks like. For example, here, PINNR is some sort of internal representation or a platform independent neural network representation that's being used within this software framework. Then the compiler will actually generate optimized code for that target device because it knows the capabilities of the target device that you're looking at. And it'll bring the best capabilities out that are needed in order to achieve the best performance from the optimized kernel libraries that are available. Remember, I talked about how the M0, the M3, and the M4, a range of different microcontrollers that have different kinds of instructional support. The reason I'm showing you this is because now you can make that connection here. Depending on the type of microcontroller, you might want to choose the right type of instructional level support in order to maximize the performance of the particular device. So you can run inference much faster. And finally, you generate the executable code that runs on the microcontroller. And this is the typical flow. And implementations vary quite a bit, but here's an example on the ST Microcontroller Framework. For example, here, if you take the model that is on the left-hand side and you run it through the STM cube, as well as you run it on TensorFlow like Micro, there are differences. TensorFlow like Micro, for example, here consumes a little bit more flash, a little bit more RAM, and therefore consumes a little bit more of the runtime. Well, this is not always the case. It's very subjective and dependent on the model you're using and the type of optimization that are supported on the platform of your liking. Well, of course, there are differences where TensorFlow Lite is positive. For example, it's an open source project and it can run across multiple platforms, not just the ST Micro platform. Does that matter? Well, it depends on your needs. But the general point I'm getting across, is it's important to understand there are many different frameworks out there, and TensorFlow Lite Micro is one that we will go into deeper. How do you choose the right framework is an important question that you should really think about down the line. And you have to think about from the hardware standpoint, from the embedded inference standpoint, in terms of the usage and the user experience in your application, in terms of do you have reduced latency with one framework versus another? And then you also have to think about it in terms of the accessibility of the experience as a developer. Now, we're going to try and convey some of those lessons through the lens of TensorFlow Lite. And specifically, we'll talk through the implementation nuances and details of TensorFlow Lite Micro, all of which you need in order to start building actual applications.